All right, so we should be recording now. So, welcome to the final exam, CS320 review session. My name's Lauren, and we have our tutor Roshana as well. So, we'll be your tutors for today. And pretty much for the next 2 hours or so, we'll pretty much go over whichever topics you want. If there's like specific questions that you want to go over, pretty much any topics that you guys want. So the exam is going to be cumulative. So it's going to be pretty much everything from Gödel numbers. So just as a quick little guide on what to specifically go over, right? Gödel numbers was like the first topic that you guys went over. You could probably expect one of those one-page questions on Gödel numbers, probably going back and forth from a Gödel sequence to a number and a number to a Gödel sequence. Knowing how to do that, knowing how to solve if they give you variables involved. So like one of those questions that has more of like x1, comma x2, dot, 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 etc. Something along those lines. And as well as the ones that divide evenly into one number, but don't go into another number, right? So there's a variety of those kinds of questions in the problem book as well as past exams. So you would definitely see something like that on the exam probably. And those are pretty easier questions too, right? They might look a little tricky at first, but once you break it down with prime factorization, then it ends up not being too bad. Then we get into what I call the holy trinity of regular languages, right? We have regular expressions, we have context-free grammars, and we have automatons. So these guys can be converted into one another if they are regular. So regular expression, obviously, given the name, has to be regular, and automatons also have to be regular. Context-free grammars, not all grammars are regular, but I can write all regular expressions as a grammar. This kind of gets us into the pumping lemma proof. And what this is essentially just proving is if something is regular or not, or context-free or not. And I have a guide on that, right? You're essentially checking for links. If something has links, can't be regular. What's a link? Well, it's something that looks like AK, BK. You have the same exponent here, right? You'd see these with what we call telescoping grammars, which is a variety of the context-free grammar. And essentially it's saying for 1A, I have to write 1B. So the second I have links like that, cannot be a regex. Now, if it's not a grammar, the two things we keep in mind, links of three, not context free. This is not good. You can't pump more than two characters at once. So these guys get pumped, this one does not. And the other thing is intersecting links. So if I had something that looked like AK, BJ, CK, AJ, we have intersecting links. This is not good because if I pump this link here, I'm accidentally pumping this guy too. So these are our two conditions for non-context free. So that's pretty much from the first exam a little bit. Sometimes it's the second exam. You got Turing machines, right? These guys come in two varieties. You'll either be asked to write out regular expressions that work for the except, the diverge, and the rejects, right? Diverge is often written as an infinity sign as well. Or you might just be asked to just straight up create strings that work as well. And that's something that is actually even easier. You don't even have to create the regex. So you can do something like that. These guys also have algorithms that are usually the last part of these questions. So if there's like 5 parts, maybe the last 2 parts are these algorithm questions. I will be honest, these are not my strong suit, but I did a little bit of research on them and I posted a guide in the server that kind of goes over kind of like a template for them. So pretty much these questions are kind of hit or miss, right? And the final topic, right? So all of this pretty much is exam one. All of this pretty much is exam two. The final topic that is in neither of them is push-down automatons. And this is the last topic that she usually goes over. I have a video on specifically that topic as well. But pretty much pushdowns are like Turing machines, but in a stack form, right? We remember stacks from data structures, hopefully. That's the LIFO structure, last in, first out. So you could think of it like a stack of pancakes. You gotta eat the top plate before you get to the bottom plates. So that's pretty much the only new topic that you guys are going to be really dealing with. Um, there might be a couple more new algorithm questions as well, but that's kind of more from exam two. So pretty much this final exam is going to be a combination of everything from exam one, everything from exam two, plus pushdowns. And it seems like a lot, but you have more time, right? You're gonna have probably like the 2 hours or so. There's going to be way more questions to choose from, and there's going to be way more points that you can get. Meaning, you do not have to answer everything. You do not have to know everything. I'm going to be completely honest. I just, I'm not that, I was not that good with like proofs and everything. The pumping lemma proof really messed me up a lot. So I didn't really do the pumping lemma proof as much when I took the class. And the algorithm questions, I didn't do those either. I focused on everything else, really made sure that I was good with everything else, and I was able to do very well. So you want to pick and choose. You will not make it through everything. So it's very important to do a lot of practice questions, work on your speed, but also ensure that you're ensuring that you have accuracy, right? It's better for you to do these four topics super, super accurate than to be kind of picking and choosing and getting through everything, but not accurate at all. Because she can and will write a garbage can on your answer. But in the end, just do the best that you can. So, answering some of the questions in the chat. We'll try to get the recording posted ASAP. As soon as this downloads, I'll have the Zoom recording on it, and it should be up to on YouTube probably within a day. So the video itself should be there. And you're welcome to record this on your own too, by the way. If you'd rather have it on your computer locally and that way you could access it immediately, go right ahead. And there will be likely more than 100 points available. So in past exams, you had like 60 points was 100, and they were like a little bit more than that. In this case, 60 points is considered the passing score. 100 points is 100. And you're going to be having like more points than that. So there's probably maybe like 125 points if I had to estimate. Don't worry about the points, honestly. Just focus on trying to do as many questions accurately as you can, right? You understand how her midterms worked, so just imagine that midterm is extended to having more questions. So, yeah. The exam might be on different days if you're in different sections. So that might be why. But we'll try to get the recording out as soon as possible. Usually it finishes processing within a few hours, so I could have the Zoom recording up, even if the YouTube is not up. But anyway, let's get started on some topics. So, you guys let me know what you want me to go over, right? I kind of have videos on mostly everything, so it's really what you guys want to go over at this point. Want to make sure, you're getting the help that you need. So feel free to post some questions in the chat, screenshots, practice exams, even just specific topics that you want. Um, and yeah. Okay, I got a request for Gödel numbers, pumping lemma and Turing machines with algorithms. Okay. Yeah, let's do some Godels really quick, and then we'll switch over to pumping lemmas and Turing machines. That's a good plan. Okay, so, all right. Just as a refresher, right, we know Gödel numbers are going to be pretty much creating an encoding scheme of a number by using its prime factorization. So usually a quick example that I like to do about this is if I take the number 24, we take its prime factorization. What primes can I break it up into? Well, maybe it's a big number and we don't really know, but I can work on dividing on what I do know. I know 24 is 6 times 4. Okay, cool. All right. Well, I know 4, well, that's easy. That's just 2 squared. 2 is as a prime, so we're all good with that. I also know that 6 is 2 times 3. And just like that, we broke this guy down into all primes. So this is 24 is the same as saying 2 to the third, right? There's 3 of these 2's times 3 to the first. There's one of these 3's. So to go from a number to a to the Gödel sequence, we take these powers and we subtract 1 from them. So 3 minus 1, 1 minus 1. This gives us a Gödel sequence of 2, comma, 0. And we use the angular brackets for that. So this is telling us that we have 2 plus 1, which is a total of 3 2's, right? And we have 0 plus 1, meaning 1 in the 3 position. And the key with these Gödel numbers is that we have consecutive primes. So this is not a problem, right? We have 2, we have 3. But if we had more, we had like a bigger number, we'd have to keep going. Let's say we have 5, we have 7, we have 11, we have 13, we have 17, etc., right? So good to know your primes. I'd say like up to maybe like 23 or so is good to know. But the key here is if I had a larger number, let's say I had 1, 2, and let's say 3, let's just say, right? This is totally fine. This is a consecutive prime. We know this is 2 plus 1. This is saying that I have 2 to the third power. I know I have 0 plus 1. This is 3 to the first. Then 5 to the 1 plus 1. This is 5 squared. 7 to the 2 plus 1. This is 7 to the third. Then 11 to the 3 plus 1. 11 to the 4. So I would take 2 to the third times 3 to the first times 5 to the second times 7 to the third times 11 to the fourth, right? We're not worrying about these guys for the time being. Multiply that out and we get some gigantic number that we don't need to worry about right now. So this is totally fine. But if, let's say, I did not have a 5 here, right? I have a gap. This is not good. We've skipped a prime. We've gone straight from 3 to 7. This is illegal. This cannot have a Gödel representation. So if she gives you a number and you take its prime factorization and you see it has 2, it has 3, it has 7, it has 11, oh, it's missing 5, this cannot be written as a Gödel number. So that is a key thing to keep in mind in this case. So that's the main gist with Gödel numbers. So you might get questions like those. You might get questions that are a little bit more involved. So let's see if I can find some of those that are a little bit more. Okay. Exam 2, exam 1. Okay, this is a good one to go over, right? So over here, this is one of these divisibility questions. We want to create a Gödel construction that follows these instructions here. It's divisible by 35, not divisible by 33, not divisible by 28, not divisible by 25. First step with one of these is you want to create the Gödel factorization for all of these guys, right? So I want to essentially take the prime factorization of them. So let me start with 35. So 35, well, I know that that is 5 times 7. 5 and 7 are both primes. Fantastic. Now, if the question was asking for the Gödel sequence of 35 by itself, notice that we skipped the 2 and the 3. This would not be legal. But again, we are creating a Gödel sequence that works for all of these guys. So it has to involve 2s and 3s in it, regardless. But we know that it must have a 5 and it must have a 7. So if I were to create a Gödel sequence that works for this, well, a very basic one would be 2. Okay, so I have my primes 2, 3, 5, and 7. And I'm just going to put zeros in here. This is just saying 2 to the first, 3 to the first, 5 to the first, 7 to the first. This has our 5 and our 7. Therefore, we know that this would indeed work for the first one. But notice, that only takes care of the first condition. I need to make sure that this Gödel sequence is not divisible by 33, 28, and 25. So if I were to take the prime factorizations of these guys, this is going to give us what we want to avoid. So 33, well, I can divide that into 3 and 11. Okay, cool, right? 28, all right. Well, let's see, 28, how about I break that down into 4 and 7, and 4 can be broken down into 2 and 2. Okay. 25, all right, that one's pretty easy. 5 and 5. All right, fantastic. So what is this telling us? I must have a single 5 and 7 in my factorization at the very minimum. But I don't want any of this stuff in there. Well, it kind of looks like a lot of mess over here. How am I going to know what not to use? All right. Well, 2 is saying I can't have 3 and 11. All right. Well, this is a bit of an issue. I need a 3 in order to have my 5 and my 7, because otherwise I can't have a consecutive prime. But this is only half of the battle here. As long as I don't have an 11, I will not have a 33, right? As long as even if I have this 3, as long as I just don't give it an 11, I'm fine. That means I cannot go to 11 in my prime factorization. I must end it here. If this was a larger number, let's say it was 13 times 3 instead, then I could have actually had a 0 in the 11 spot. That would have been totally fine. But this is saying I can't have an 11 because I already have a 3. The second I have that 3, I can't go any further with that. So I have to stop my factorization after 7. Cannot go to 11. All right, that's a second condition that's handled, right? So I know that I'm limited to there. So that's going to handle that guy there. Now my third condition is saying I have 7 and I have 2 and 2. All right, well, this is another problem point because I know I need a single 7, right? That's literally the definition of this guy. And I need to have 2 in here. But this isn't just 1 2, it's 2 2s because it's 7 times 4. So similarly, where I can't have my 11, I can't have 2 2s. So I can only have 2 to the first here. I cannot have 2 to the second, let's say. So in a case like that, we want to make sure that we're only using what we can actually afford, right? We need to have the 2 to make this consecutive, but I can't have a second 2. So this has to be hard-coded as a 0, just like this has to be hard-coded to end after my 7. So that's what this third condition is telling me. I can't use 2 squared or any power higher than 1. Okay, all right. So we know that this guy is hard-coded where he is, and this line is hard-coded where he is. Finally, the fourth condition is telling me I can't divide by 25, meaning I can't have 5 squared. Similarly, I must have a single 5 in this location, right? 5 times 7 gives me my 35. But likewise, I cannot do 5 squared. So this guy is also hard-coded at 0. All right, so we need to find other Gödel sequences that work. Now that we have our 3 rules here, right? So we know that these two are hard-coded, but you know what isn't hard-coded? These two. So I can make any combination that has 0 here and here, right? And was 0 in the 2 spot, a 0 in the 7 spot. Oh, sorry, a 0 in the 5 spot. But I could be flexible with what's in my 3 spot and what's in my 7 spot. So I could do 0, 1, 0, 0. I could do 0, 1, 0, 1. I could do 0, 5, 0, 5. I could put anything I want in these spots as long as these two are good. So that's pretty much what we're doing with these problems. You take the prime factorizations of all these, you find what you can change and what must stay consistent, right? And sometimes these might not work. If they don't work, just show why they don't work, right? If I literally couldn't create something, if let's say instead of being 2 and 2, if this was a single 2, well, that's not good because I need to have a 2 anyway. If I have a reason that I can't have something work, then boom, it doesn't exist. Yeah, so those values can change because our limitations tell us the following things. It tells us we need to have a 5 and a 7, right? The second condition tells us I can't go past that 7 because then I get into 11. So I know I'm going to have 4 Gödel sequences. I'm going to have 4 numbers here, essentially, the 4 first primes. Third is telling me I can't have a second 2, meaning that this is hard-coded at 0. It must be 0. Similarly, 4 is telling me I can't have 2 5s. This is also hard-coded at 0, right? 0 meaning exactly 1 2 and exactly 1 5. There was nothing telling me that I can't have a larger number in my 3 and my 7 spot, right? I could have larger than 7. I could have 7 squared, 7 to the third, 7 to the fourth, etc., because everything has at least one 7 in it. So you find the parts that you can change and the parts you can't change. You could be as creative as you want. So these are just suggested answers, right? You could use anything as long as you keep the first and the third 0 to work with that problem. So this is like a very common question that you might honestly see. And you can pretty much have any types of divisibility in this case, right? I bet you if I scroll down a little further, another one, right? So again, you find the divisibility, right? You know it has to be divisible by 10. I'm not going to do the whole question here in the essence of time, but I know that 10 is 2 and 5, meaning that my Gödel sequence must have a 0 in the 2 spot and in the 5 spot. But we know we can't skip primes, so I need a 0 in the 3rd spot. Then I take the divisibility of all these guys, right? For instance, I'm just going to do 14 is 7 and 2. All right. Well, similarly to the previous one, I need a 2 in this spot. It's literally defined indivisibility by 10. But if I have a 7, it's game over. I'm now going to be divisible by 14. So this is telling me that I'm ending right here. I cannot go to the 7 spot. Otherwise, it violates principle 2, right? And continuing on and on through that, right? 24, we know that became 2 to the 3 times 3 to the 1 from the previous problem that we did. So again, I must have 3 here. It's defined. This is telling me, though, I can't have 2 to the third. So this is telling me I could have 2 to the 1 is fine, right? I need that. I could have 2 squared. That's fine. But the second I get into 2 to the third, it's not good. Meaning this guy, instead of hard-coded as 0, is hard-coded as 0 or 1. So I could change this to be 1, 0, 0 or 0, 0, 0 from these first 3 components here, right? And you know what? I'm just going to finish off because there's only 2 left. 25, we know this is 5 squared. So this is telling me, right, this 5 cannot go to 2. It is hard-coded at 0, just like with the previous one. Because if I have a second 5, boom, it becomes divisible by 25. And finally, 27, right? So I know 27 is 3 times 9, or technically just 3 cubed to keep it simple. So similarly, 3, I could have 1, right? 3 to the 1 is fine. 3 squared is fine. 3 to the third, not fine. So from this, right, we can create a bunch of things that work. For instance, the ones that she used, 0, 0, 0, totally fine, right? Does not violate any of our terms. 1, 0, 0, right? I said having a 1 here, meaning 2 squared, that's fine. I just can't have 2 to the third, which would have put a 2 in the 2 spot. And 0, 1, 0, right? I could put a 1 here. We said 3 to the 1 is fine. 3 to the 2 is fine. I can't do 3 to the 3, meaning I can't put a 2 in this spot. And pretty much, yeah, I could have done a 1 here and a 1 here if I wanted. That's another one that would work, right? It's just making sure that given these guys, you make sure it's divisible by that, not divisible by any of these guys. Yeah, exactly. That's a very great point, Joe. There's 4 possible solutions in this case. So if she asks for more than 4, then it's impossible, and you can use that as your reasoning. Yeah, that's absolutely right. So on some of these that have a little bit of a smaller number, you're going to have less degrees of freedom than you would in the previous question, right? We were dealing with bigger numbers. There were much more combinations. Here, I only have 3 numbers, and I know that I can't make the 2 spot and the 3 spot greater than 1. Otherwise, we have problems. Oh, yeah, literally right over here. State the cardinality of set S. What is set S? It's just literally the set of Gödel sequences. And we've come to the conclusion that we can have up to 4 of them. We could have this one, and then the other one that I could have done is 1, 1, 0, right? And you could use that as your reasoning for that, which is literally what is said here, right? So yeah. She wouldn't ask for the cardinality of something really big. It would be something much smaller like this that could actually be done, right? But you're trying to find every combination of it. So that's a very interesting question. I don't think I've seen one that had this cardinality part to it before. But, if you understand this, you can apply it to anything else, even if she decides to surprise you on the exam, right? That's the key. You don't want to memorize, you want to just know how it works. Okay. Yeah, so that's pretty much Gödel numbers in a nutshell. Sometimes they have placeholders, right? If you have something that has a placeholder like x1, comma x2, comma x3, just know that these are some numbers. If I want to combine some set that's given, right, by placeholders, and let's say a number, let's say our good friend 24. I don't know why I like using 24 a lot. I guess it's just kind of easy to think of, right? We know that's 2 to the third times 3 to the 1, which is just the Gödel sequence of 2, 0, right? I take these exponents, I subtract 1 from them. So what I can do here is I know that this set here has x1, x2, x3. This set has 2 and a 0. So I want to make sure that I have 2 times x1, right? I want to make sure that this 2 is involved here. And I want to also make sure that I have 3 times x2, right? We're combining these guys. Anything else that's given, there's nothing here, so I just have x3 here. Very similar to the previous problem where we're combining various divisibilities. We're making sure that we're combining our x1, x2, x3 from the set that's given, and our 2 and our, wait, I'm sorry, that's supposed to be a 0. Actually, oh, it's 2 plus. I'm sorry, because this is the Gödel sequence, right? This is our Gödel sequence, not the actual prime factorization. So I'm saying 2 from this plus whatever number is in here. X1, x2, x3 are just placeholders. Let's say this is 3, this is 2, and this is 2, right? This is literally saying 2 plus the existing 3 here. This is 0 plus the 2 existing here. This is x3, which there's nothing there, 0 plus the 2 over there. So if you ever see something like that, just know that these guys are just placeholders. But that's cardinality in a, not cardinality, sorry, Gödel in a nutshell. Okay, so cardinality usually is not a topic on um, the spring and fall exams. Um, Usually it's more for summer and winter. So I'll say that if we have some time at the end, we can go over it, but I wouldn't worry too much about it. There are a couple of videos on counting principles, so I would recommend kind of going through those and just having like a little knowledge on that, but I wouldn't really focus too much on that. You're better off focusing your energy on the stuff that's guaranteed to be on the exam. Like we know there's going to be a ton of regex, there's going to be a ton of grammars, there's going to be a ton of automatons. Like this, the Holy Trinity, really, this is going to be like the bread and butter of the exam. So I would recommend kind of focusing our energy more on that kind of stuff. Pumping lemma as well. This is a exam one. So yeah, we could definitely go over regex. What I'm gonna do is I'm gonna find one that kind of has, yeah, I'm gonna find one that has like pumping lemma in it so we can practice regex and pumping lemma at the same time. Okay, so a lot of these over here, we can kind of see there's like a variety of like these kinds of questions that look like they have two parts, but in reality, you're only answering one. So the good part about these kinds of pumping lemma questions, right, is that you decide essentially whether or not you're going to be using the proof or making a language. So if you're good with the language, focus on the questions that use the language. If you're good with the proof, focus on the questions that involve the proof. So let me find one that has more of a regex on it, if possible, because I know a lot of these seem to have like grammars and stuff. Automatons. Yeah. Okay, this seems to be mostly our grammars. Um, all right. Well, I do want to kind of just take a look at something like this over here, right? So this problem over here, I have these various letters going to different powers. Now, this part is fine. There are no links between the characters. It's not like there's a K there and a K there. That would immediately be a link. We're asked to prove if it's regular, right? So the key with regular, the second you see a link, not good. But this down here establishes a link. K is equal to L plus J plus M, meaning that this K is literally L plus J plus M. Now we see these guys are creating links with those guys. That is no longer regular. So the second you see any relationship, right? Maybe instead of being addition, it's saying that K is equal to L times J, or maybe K is equal to L. Any of that, right? This is immediately a link. So this is not going to be regular. We are not creating the automaton for it. Because remember, automatons and regex are done when we have a regular language. If it's not regular, I cannot create a regex or an automaton. I may be able to create a grammar, right? But the question itself is saying regular, right? If it was asking for context free, I would have just made a context free grammar here and we wouldn't have needed the proof in that case. But for this, we're going to be using our proof. So you would probably not be given this template on the exam, right? Let me find what the blank one, right? This template, you might have seen it on exam two. Sometimes she hasn't been giving it on exam two either, but you're definitely not getting it on the final. So you're going to just have it looking like this and saying, if L is not context free, then just do a proof, but not complete the missing parts of the text. It'll literally just be blank here. So you'll fill in this blank with either your grammar, your automaton, your whatever, or the proof. So going back to this guy over here, right? We see that we have our link with K. So we know the first part about our proof is we want to create a characteristic property. What is a characteristic property? It's literally what is violating our regular language. And we know regular languages, violation, it's a link. So we're going to show that this over here is our characteristic property, basically, right? So the way that she has it worded is that the number of G's is equal to the number of B's plus the number of C's plus the number of A's, which is literally just saying this over here. Again, you don't have to say it exactly the way that she says it. You want to say, yeah, that's great, Joe. Property, number of G's is equal to the number of non-G's. That works too, right? You're just verbally stating this property. All it's just saying is that number of G's, right? It's saying G to the K is equal to all the other letters pretty much summed up in a sense. So that's our characteristic property. Now, right, we're going to actually create our pumping lemma proof from this. So we assume the opposite, that L is regular. This is what we call a proof by contradiction, in the sense that we try to show, hey, if L is regular, then it should work if I were to pump both sides. And then we realize that it's not the case. Because if I pump only one of these guys, only one of the, let's say, BL, CJ, AM, and I don't pump this G in return, I'm going to break the link between these guys. And that's proving the second I have a link, it's not regular. Because we can't control that, right? Regular expressions have a star. They're not defined as a nice telescoping grammar that can actually handle this kind of link between them. So we're going to define a pumping constant. It doesn't have to be P, you could use pi, you could use really anything. So, don't worry if your syntax isn't the same as her syntax. But essentially, our constant is basically how much we're going to be kind of pumping on each side, right? It's just some constant, some number, right? Use a garbage can as the constant, imagine. That would be funny. Yeah, use like some letter, use some like Greek number, letter, whatever. Doesn't really matter. Just make sure it's not something that stands for something else. Like, don't use like a lowercase letter that's used up here, right? Because then that's going to confuse it with the other stuff. But I could use like if I wanted, P is not in this, right? So she used P. I could use like I could use X if I wanted to, Y, Z, whatever. Doesn't really matter. So the first thing we have to do is we have to create a base case. And that's going to be our W0. So W0 is trying to, in her words, get rid of all the garbage, the stuff that we don't care about. We want to really just focus on the characteristic property itself. So we have GK, which is all of our G's, right? Everything to the K power, and BK is just all the other crap, right? We could use B's, we could use any of these guys, really. I could use C, I could use A. It's just showing that I just need to show the link between one of these characters. I don't have to show the whole property. I just have to show even K is equal to L, right? K for the G, B, and the L. If I show there's a link even between two characters, immediately it's not gonna pump correctly. So in this case, she uses B. Could use any of them, doesn't really matter. So we're kind of just showing in this case, right, that our K is greater than our pumping constant. Because think about it. If our pumping constant is smaller than the whole string, it's going to show that if I pump this string, right, I'm only pumping a piece of it. I can't pump the entire string. If I put a star on any of these guys, it's not going to pump the same amount as something else. If I have G star and B star, there's no way to control that's the same. That is the limitation with regular expressions. So we know that W0 must pump because we take the cardinality of this guy, right? We show how big our string is. And in this case, right, if we pump this once, we're going to end up getting 2 times K, which, it's because we have 1K here and 2K here, right? G to the K, B to the K. So I'm showing that, hey, the length of the string, which the base case, W0, is just 2 characters, is going to be greater than if we have 2 of these guys to the P power, which is based on our pumping constant, which is pretty much what I had said, right? That we're going to be pumping more characters than our pumping constant can handle. So because this is going to be too big compared to this, it's going to end up breaking our characteristic property. Can we say G to the K, B to the L, C to the 0, A to the 0? Yes, so that's kind of what's going on behind the scenes. We're essentially getting rid of our other variables here. Okay, we have someone that's lost. Don't worry, don't worry. This is a difficult proof. It's hard. It's a lot of stuff going on. So don't beat yourself up, pun intended. So just to kind of go over what we've done, we've seen there's a link. We've defined what is the link. That's just a characteristic property. And this is just saying the number of G's is equal to pretty much the sum of all the other letters. Right? That's what this is saying. And you could literally just say that too, right? It does not have to be exactly her words. So we're going to define a pumping constant, right? P, just a pumping constant. It's how much we're going to pump on each side. And the key here is that this constant is going to be much smaller than the length of our string. We create a base case, W0. This is going to just be our smallest case that we can think of. So I'm going to just take 2 of these guys, right? I'm not going to end up taking the whole string, right? Because there's too much stuff going on here. I'm getting rid of the C and the A. And I'm doing this by setting J equal to M equal to 0. So both of these guys, the J and the M, are going to end up just being 0. So if I have C to the 0, A to the 0, these guys cancel out and I'm only left with my G and my B, right? I'm only showing the link between 2 of these guys. So I'm just simplifying the string, right? We're just showing that there's clearly a link between the G's and the B's. Now, this is where we're going to show that the length of the string, right? 2K. Why is it 2K? There's one character here, one character here. Whatever K is, I multiply that by 2 because K is to the G power and to the B power. So I'm showing that this length of my string is always going to be greater than the same length of my pumping constant, right? If I set this K to P, we know that P is always going to be way smaller. So I'm showing that that pumping constant, P, is going to be smaller than 2P, right? That's as if these K's were replaced with P. And that's smaller than 2K, which is the actual length of the string. So now, right, we're showing that we have our pumping window here, right? The pumping window is actually showing us where we're going to be pumping. So pumping constant, pumping window. Pumping constant is how many letters we're, I guess, pumping in a sense, right? That's always less than our cardinality. So if let's say I'm pumping 2 characters, right? P is less than 2. So let's say P could be like 1 character. So our pumping constant is always going to be way smaller. And we're showing, right? If you have 1 box, I can't store 2 things in my 1 box. That's really kind of the gist of what's going on here. So the pumping window now is showing that if I have G to the K and I have B to the K, think about what's going on with the regex. If I made this a star and this a star, that star only is applied to each character individually. That means if star on this side is 3, but star on this side is only 2, these guys are not going to be equal. This is going to end up violating our property that they were supposed to be equal. So that's what we're showing here. We're creating a pumping window Y, right? And this is just saying where we're going to be pumping our string, right? Where we're putting that star on, in a sense. And essentially, right, this is going to be equal to G to some J power. So all we're showing is that we're going to be pumping this multiple times. You could think of this J as literally a star, right? So our J is going to be equal to our star. And we're showing that, hey, if I pump this side, right, if I have a star on this star cannot be equal to this star. So that means that the window of where I'm actually pumping that amount of times is only on the G's, right? So that's what we're saying down here. The pumping window is entirely within the G's because it's only fitting within the first P symbols, right? Pumping constant is how many symbols we're pumping. So I can only pump the G's. I can't pump the B's too. The way I like to think of it is imagine you have a towel, right? And it's kind of a small towel. It's like one of those small beach towels. Your whole body is wet. You just got out of the pool, and your towel can only dry half of your body. It can't dry the other half of your body, right? So that's what's going on here. I can pump this side, but I can't pump this side. My towel, my pumping window only fits over there. So now we need to actually give an example of this, right? So we're up to here. This is the part that's a little bit more intuitive, right? We're going to pump up once, meaning we're going to generate more G's. We're going to pump whatever's in our window. We're going to dry half of our body, let's say. Now, this is going to be a problem because notice, if I pump J times, J being our star, I'm going to duplicate this guy, star, or J number of times. So for the example of this, let's just say this is equal to 2. I'm going to pump this guy up twice. So I'm going to say G. I'm going to pump him once. I'm going to pump him twice. Did I pump this guy? I don't think so. The link has been broken. That's what we're showing here. Now it's going to violate our characteristic property. The number of G's is not equal to the number of B's plus the number of C's plus the number of A's. Remember, we set these guys equal to 0 at the very beginning. So the number of C's and the A's, that we don't even need to worry about. We're just focusing on the number of B's, which is what we assigned up here. That's the purpose of creating this W0 string. We want to simplify things. Get rid of all the stuff we don't care about and just create a single link. And just as we showed here, we pumped this guy, we did not pump this guy because our pumping window can only extend to the G's. That star over there, that number of times that I'm pumping that guy, is only on the G's, not on the B's. So this is going to end up showing why we can't have a link with regular expressions. So that's pretty much the gist of doing pumping lemma with our regular expressions there. I came up with the phrase PCS, pump it up, meaning define the property, define a constant, create a valid string, and then pump it up. Yeah, that's really great. So Joe was saying how he created this phrase of PCS and then pump it up. Right? So P, create a characteristic property. That's the first step. You got to see if there's a property that's going to break this thing in the first place. C, I define a pumping constant, right? I'm going to create that pumping constant there. That's going to be the number of times that I'm going to pump this guy. Then I create a string, right? That's the S. That's what we did over here. We did the W0, right? That's going to be our base string. Now, pump it up. Show that when you pump this guy once, it breaks our characteristic property. Yeah, characteristic property is just showing the number of G's is equal to the number of B's plus the number of C's plus the number of A's. In other words, right, we know that we had G to the K, B to the L, C to the J, and then A to the M, I think it was. K, this exponent is equal to L plus J plus M. This is the link. This is the characteristic property. You say the characteristic property in words. That's what we're doing right over there. Right? So the number of G's defined by this K is equal to the number of B's plus the number of C's plus the number of A's, because this K is defined by these three variables. This is our link. Right? Characteristic property, link, same thing basically. Okay. Any other questions? Yeah, absolutely. So again, think of the pumping window as like that towel, right? That pumping window, that star can only pump this part here. So we define our pumping window as where our so-called star would be defined, right? So if I wanted to say G star, right? I was making a regex on this, right? This star is not equal to, say, this star over here. So we know that the window of what actually gets pumped from one star is only within the G's. Or we could move the window here instead and say only the B's get pumped, right? But regardless, we end up with the same thing here. Instead of maybe GGG, maybe it's G and then BBB if I pumped the B's instead. That works too. But our window is showing where our pumping constant is defined. Pumping constant is just another way of defining a star. We're just setting it to be some variable. And I'm just showing that I'm pumping this guy however many times. Yeah, no problem. So the best way of doing like practicing these guys is just exposing yourself to a lot of different problems. Right? This is one way of doing it. Maybe a different problem would show it like a different way. But you're going to see it's the same idea that's going on, right? So over here, right? Oh no, it looks scary. It's a string that's equal to 4n plus 5. Oh my gosh. But look, we're still proving the same thing here. Is it regular? Is it not regular? So let's take a look at this, right? We have a language over these four characters that consist of exactly those strings whose length is equal to 4n plus 5. For some natural number, n is greater than or equal to 0, but the three symbols in the middle all equal b. Okay. There are two things going on here, two properties to keep in mind. Length is equal to 4n plus 5. Okay, I don't care. I could define that with the regex, please. 4n would be four characters in a star, right? I'm just going to use sigma to denote the characters, right? So four characters, sigma, 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 and put that in a star, right? To show 4 times some n denoted by a star plus 5 extra characters on the end. Sigma, 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 sigma. All right, that's not a problem. And I know it's asking for an automaton, but we know we can convert between automatons and regex easily, but just showing what a regex would look like. So this has passed the test, but this is the problem. There's a second thing. The middle symbols are equal to B. We cannot control the middle symbol in a regex. Just like with the previous problem, right? Star. I don't know what the star could be, right? Here, I don't know where the middle symbol is going to end up being. Even if I put a symbol here, right? This is saying this over and over again. So I'm going to end up getting sigma, sigma, some middle symbol, sigma, sigma. Then again, sigma, sigma, some middle symbol, sigma, sigma. This is not in the middle anymore. The middle was changed to like around here. Anytime that you have a middle symbol, that should be a red flag. But here's the thing, right? Middle symbol can be composed when we have a finite string, right? The problem here is whose length is equal to 4n plus 5, meaning that, look, I'm pumping this guy multiple times. This middle symbol is changing. But if it was only, let's say, 5 characters, 5 is finite. I can just straight up code a regex easily on that. Sigma, sigma, middle symbol, sigma, sigma. That's totally fine. Or even 3 symbols in the middle, right? Boom, done. Easy peasy. The problem is this is an infinite string with middle symbols. This is telling me it's infinite, right? That's what we have here. The second we got a star, we cannot control these middle symbols. So immediately, that's a red flag. Infinite string, middle symbols, not regular. Okay, so Joe brought up a to the 2n, BBB, c to the 2n. Okay, this is the problem though, right? What did we bring into the picture, right? You wrote out a to the 2n, BBB, c to the 2n. That is a link, just like the previous problem. We can write that out as a grammar. That's not a problem at all. We can totally do that. But the question is asking for a regular expression. I cannot control these guys here. So immediately, I got to switch gears to my pumping lemma proof. So same thing. We're going to use that same strategy, right? PCS, pump it up. Characteristic property, right? P for property. That's the first thing. What was the property? Well, we need to control that the middle symbol is, what was it? Not B or something, or it was B. are all equal to B. It literally doesn't even matter what that is. It could be equal or not equal to, or it could be anything. The second you hear middle symbols, immediately red flag, right? So she could reword this problem with anything in the middle. So, like, it could be literally anything and it would still work. So, we have our property. The three middle symbols are all equal to B. Also, there's a second property that the length of the string is odd. You don't really need to even say this, honestly. Just say the three symbols in the middle are all equal to B, and just say something about the string being infinite. That's what I would just say, honestly. Literally, you're just restating the question, like what the properties of the question are. So those two properties that we went over, it's finite, and we have to control the three middle symbols. That is your characteristic property. It is the property that is showing that there are links. So we're going to continue, right? We're creating our constant, right? So we did our P, now we're doing our C. So we're going to create our constant, and they use T, you could use P, you could literally use anything. Just keep track of whatever she's using. And if you ended up using a different constant, like just try to translate it back and forth. So know that T is our constant. So if I had a string, right, T is like the star, let's say, how many times that I'm pumping something. So I know I defined a regex for this guy to be like sigma, 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 and this thing was star, right? So this star is literally our T. It's how many times that I'm pumping this guy up. So create our string, right? We did our C. Now we create a valid string. Make your W 0. So what we're going to do here is we're showing, right, that I have three symbols in the middle that are B, right? We want to create our good string. Then, what is it also saying? It has to be 4n, right? So 4n plus 5, technically, right? So if I have 4n plus 5, well, let's say 4n plus 5 will make n equal to, let's just say 1 in this case, just to kind of visualize it. So that means that I have 4n plus 5. So 5, 1, 2, 3, 4, 5, and then four more symbols. 1, 2, 1, 2. So now, right, this could be written as these three symbols are our B's. We know that. How many are left? 2n, 2n, plus 1, plus 1, right? These two and these two are coming from my 4n part, right? These and these are the ones that are being pumped. The middle symbols, though, are not being pumped. These are the plus 5. These are the middle symbols that they're just stuck in the middle, right? We don't really care too much about them. But we're separating it because 4n is not just being pumped on one side, it's being pumped in between because we have to control where the middle is. So we have 2 of the 4 on this side and 2 of the 4 on this side. So you could think of it as 2n, right? 5 symbols, and then another 2n, right? But the key is, all right, 3 of the 5 symbols are being defined as B's. So we can rewrite this as 2n plus 1, 2n plus 1, and these three are our three B's. So we broke this down into 2n and 2n, right? Then 3 B's. What's left over? Well, that just becomes the 2n plus the 1. So this is going to be our W0. So we have created our valid string. Okay, let's take a minute. Is Turing machine an easier topic than pumping lemma? It's honestly very subjective. So, if you're good with like the proof, if you're good with memorizing the proof, pumping lemma might be easier. If you're better with following a Turing machine, maybe Turing machines are a little easier for that. I would recommend try both, see what you're better at, prioritize what you're better at. You can honestly skip a topic or two and still be totally fine. And again, if you feel like, oh my gosh, I don't get the proof, but are you good with the Trinity? Are you good with regular expressions, grammars, automatons? Could you have made a grammar on this question, right? Could you have done a regex on this question if it was valid to do so? Then know when not to use the proof. I stress that so much. If you don't do well with the proof, just know when not to use it and you have an exam one question. Because these questions, they also test your knowledge. Do you know when to make the language or use the proof? Even if you don't know how to use the proof or how to make the language, just do the one that you can do. Yeah, you have to pretty much memorize the template. Um, there's one that's a little bit easier to see in the server itself. If someone is able to post that in the chat, that would be helpful. Um, but you don't have to say it like word from word. Like I kind of was like doing it in my own words as I'm explaining it, right? I don't need to say it in her language precisely. For instance, like this characteristic property, say it in plain English, right? We know, okay, the middle symbols, those three have to be B. And we know that it's an infinite string. Right? That's my translation. All right? You translate it to however you want to do it. And also know that there's partial credit. Listen, if you can, after finding the link, if you can only do like part of it, do that. Right? Do the questions that you know you can do, then try to get as many points as you can. Right? If you could just do the characteristic property, how many points is this question? Like, I don't know, like 10 or something, probably. Yeah, 10 points. Right? Okay, maybe you don't get all the points, but you got a couple. All right. 2 points is better than 0 points. So just do whatever you can, right? Even if it's not a perfect proof, like just write whatever you can. Maybe you understand the pumping part itself too. Just do those two parts, right? Partial credit's better than no credit. Would you give us points for an informal proof? Like if you just say you cannot control which characters are in the middle of an arbitrarily long string constructed through a regular expression. Yeah, I would say so. You won't get full credit if that's your entire proof, but if you just take pieces of this and you don't have a complete proof, you should be able to get partial credit. Again, prioritize the questions that you know you will do well with. If you are really worried about pumping llama, save it for the end. Yeah, the 2n plus 1 part is kind of confusing. So let's go through it one more time. So we see that we had 4n plus 5. And we know the three middle characters have to be B's. So I'm going to start out by creating a very base case. I'm going to just create n is equal to 1. Okay. So if n is equal to 1, this is telling me that I have 4 times 1 characters. So it helps to draw these out. 1, 2, 3, 4, and then, right, plus 5. 1, 2, 3, 4, 5. Okay. So this is the total number of characters. I have 9 characters in my n equals 1 case. What do I know about this? The three middle characters are B's. Okay. Now, I know that there are 4n characters that are being pumped, but I have 1, 2, 3, 4, 5, 6 characters that are left. 2 of these characters come from the plus 5, right? This character and this character are not being pumped. These characters are coming from the 4n plus 5. So we're just kind of shifting where things are kind of going in this regard. So we're showing that this is 2n, this is 2n, and what's left? Just 1, plus 1, plus 1. So this is the same as this, except we're just showing that 3 middle characters are B, right? And also, this plus 1 and this plus 1 could have also gone out here too. That's honestly totally fine as well, right? I'm just showing that I have 2n plus 1 characters that are left on the outside after defining that these 3 characters are all B's. Okay. Yeah, we'll move to Turing machines right after this. I just want to finish the problem super quick, and then we'll focus some more on Turing's. Alrighty. So we've defined this as our characteristic property, and we've created a sample string, right? This is the a to the 2n plus 1, b, a to the 2n plus 1. A is just some character, right? We don't care what a is. The only character that was defined was that we needed b's. So we have b, and everything else here and here gets defined on the outside. Yeah, I could have created n equals 0 as well. If I created n is equal to 0, then this character and this character doesn't even exist, and I'm only left with 5 characters, right? That makes sense. 4 times n. If this was 0, I'm left with 5 characters. So I literally have B, and then a character here and a character here, right? So that's also another way to visualize it too. W0 is just visualizing the shortest string that you can kind of think of in this case. So now that we have a string, right, we're going to create a pumping window. And this pumping window, right, is pretty much only going to be able to extend to our n component, right? Think of the towel or the star. The star is only good for one of these components, meaning that if this side is pumped, guess who is not pumped? This side. And if this is not pumped the same number of times as this, we lose track of where our middle is. So by pumping one time, I'm only going to pump this side, right? So if let's say I start out with 1, 2, 3, right? 4, 5, 6, 7, 8, 9. These are our B's. These are the 2 characters I'm going to pump. I'm going to pump this once, meaning I'm adding just another 2 characters. These are not in the middle anymore. Thus, it violates the pumping lemma. That's all this is saying. You could show it. Just show it. You don't have to write it out crazy like this, right? This is just showing that I have 2 extra characters on this side by pumping these 2 characters exactly once. My middle is not preserved. To preserve the middle, I would have had to pump this side in return twice as well. So that is the key with these pumping lemma questions. Pump means to expand, telescope once. Yes. So going back to telescoping questions, pumping, telescoping, same exact thing, same exact property. And our pumping lemma, I'm sorry, pumping constant is telling us how many times that we're pumping this, right? So you could think of a star being equal to like 2. Or if we have like n, let's say n is equal to 1, pump once. N is equal to 2, pump twice, etc. Any other questions on pumping lemma before we go on? We have time to go over some questions from exam 2. Um, Send them in the chat if you have some specific questions. I've just been kind of using whatever exams I've been kind of popped up on. So let's spend some time going over some Turing machines. And we'll try to go through some of the algorithm questions now that I have a bit of a guide on how to do those. Because honestly, before I really didn't understand kind of what was going on with those, if I'm being completely honest. So I would prioritize the other stuff. All of these exams are on Discord, by the way. If you need to know where they are on the Discord, oop, I'm still in the pen. Okay, here we go. Right. I revised the server a little bit, so all of your old exams are right here, right? And there's a drive right here with the most up-to-date exams, right? Problem book is still here too. Anything that you need. And if you need some of the very old exams, I don't know why you would, but there's other stuff in this server as well. But this is where all the old exams are going to be. Okay, this is what the I've been kind of trying to create these little study guides here. So this is like kind of a guide on the algorithm questions, but if you're kind of questioning what those are, it's these over here. Which language, if any, does the Turing machine M decide? Explain how to construct an algorithm that solves the following problem. These things. They're at the end of the Turing machine questions. And honestly, I've kind of been saying just disregard them, but you probably saw them on exam two, and you're probably like, what the heck is going on? So honestly, with a lot of these, it kind of comes down to remembering the pattern on this. Yeah, it's related to Turing machines. So you're always going to have questions that are going to say create L accepts, create L rejects, create L diverge, or create some random strings that work for them, right? But usually the last two or three question parts are going to involve these algorithm questions. Right? So some of them are a little bit more simpler, some of them are very complicated. But there's a little guide here on can we build the algorithm from it, right? So kind of going on a little bit of it, right? What I did was I kind of fed some of the exam questions that, we were struggling with into AI to kind of like see what the pattern is. Because AI is great on recognizing patterns. Like if you ever get stuck on even the pumping lemma questions, put a bunch of them that you're struggling with into AI and be like, I am struggling with step X, maybe recognizing the characteristic property. Show me a guide that goes over how to get the pattern from this. So, similarly, right? Let's say I have one of these questions for a Turing machine, right? I got this Turing machine over here. We can go through it as well, by the way. But I just wanted to quickly do a little overview on these guys. That way you're able to kind of work on some of them yourself from there. Explain how to construct an algorithm that solves the following problem. If such an algorithm does not exist, state that it does not exist, prove your claim. Input is a Turing machine T that decides a language S and a string W. Does W exist, right? That's what this is saying, on S complement. So what we want to do here is, right, T is the Turing machine that decides a language S. So if S is the complement on it, it's the complement of this Turing machine, right? So that's what we're saying over here. Simulate T on W and return the negation, right? Negation, complement, same term of T's decision. Observe that T must halt on W since T halts on every input as it decides S. What does halting mean, right? Well, if we have a Turing machine that did not have a final state, we can either halt or diverge. Diverge meaning we reach a blank. Halt is everything that's not diverge. So in a case like this, right, this specific Turing machine never diverges because we never get blanks going to the right. So if we notice, there are blanks going to the left, but this is not a diverging state. Blanks going to the right is a diverging state. I say it as if you get stuck inside of a black hole, right? You're stuck in a loop of blanks forever and ever and ever and ever. This is just putting a single blank down and moving to the left. If this was going to the right, then we would end up diverging. So because this never diverges, it only halts, right? Again, halt, diverge, they're opposites. So if I never, can you go over this question from the beginning? All parts. Yeah, sure. So let's go through the question before we get into this stuff, because then this is going to kind of be a little confusing. So we're asked to create the Turing machine on this guy, right? So over here, I'm given f is equal to the set t, and sorry, the final state is going to be our t, right? So that's saying our final state is right here. This is my destination. If I reach this final state, I accept. Okay? So I accept if I reach my final state. I diverge if I reach blanks going to the right. And reject is everything else. So Usually accept and diverge are the easiest because reject and halt, if you're doing one that doesn't have a final state, are kind of like the complements of them. It's everything that isn't accept or diverge. So let's focus on the ones that we know our destination. So first of all, diverge. There are no blanks going to the right. If this looks like that instead, if it was X, B, Y, B, and this was going to the right, then that will diverge. But because that does not diverge, the diverging is just the empty set. There is no string that gets this to diverge. If there was, let's say, um, over here that this was going to the right, or if there were blanks going to the right somewhere else, then you would find the regular expression that reaches that point. So let's focus on the accept for the time being now. So accept, I want to reach this as my final destination. So I start out by going to my starting state. What's my starting state? It's going to be state Q. That's what we have right here. So our starting state is defined right here as Q. So we know we're starting here. So when I'm here, I have three possibilities from state Q, right? I can go to state X if I have either an a B, or a C. So I'm going to draw out a tape over here and say to get from Q to X, right? I need an a B, or a C. Now, I am going to write a capital a capital E, and a capital K for each of these guys. So the first set of characters is the reading characters. This is saying if I see an a B, or a C, I go to state X. But we have to write something on the tape. This is going to be a capital A if it's a lowercase a that we read, a capital E if it's a lowercase b that we read, or a capital capital K if it's a lowercase c that we read. So this is what we're reading. This is what we're writing. So that's a good guess. Very good guess. Um, so after you do a bunch of these, you can kind of see where things are going. And as a bit of a spoiler alert, right? Why are we writing these characters here? Well, notice that what do I need to read in order to get to my final state? It's going to be a capital E. So this is going to tell me later on that you need a lowercase b in order to later on read a capital E out of this, but we'll get to that in a minute. So now we're in state X, right? So now that I'm in state X, we're right over here. So now the next couple of states, I see that I can loop onto state X if I read an a B, a C. Okay, now that I'm in X, this is saying A or B or C, but notice it's a loop, right? If this was like an automaton, right, we would go from Q to X and then we loop on X, right? So just like with regular old automatons, this would just be A or B or C star. So now that I secured that, I'm ready to move on to the next part, right? How do I get out of this X if an A, a B, or a C give me a loop? Well, I have to go to this final state. This is saying read a blank, write a blank, go to state Y from the left. So notice blanks to the left are going to end up looking like this. I'm going to draw a line. I'm going to put a blank. And this blank is like the end of a sentence. It's like a period at the end of a sentence. This means that this is the end of the string, right? I'm not doing an infinite number of blanks to the right. This is ending it and moving me to the left now. That means I'm entering state Y from the left. So I'm going to move this part down a little bit just because we're going to kind of be rewriting what we were doing here. So this was the right, this was the A, the E, the K. Okay, so now we're going to the left. So the way I like to think of it is imagine you're doing a multiple choice exam. You answer it once. Now you go backwards and you go over your work. You say, okay, I answered B on this one. B is the answer. Check. I answered C on this one. C is the answer. Check. I answered A. Uh-oh, B's the answer. I gotta change my answer. That's what's gonna happen here. I'm gonna look at my first character that I see from the left. That's gonna be somewhere around here. And we know that that's gonna be within this loop. So it has to be some A or B or C. Okay, well, this is saying I must have a B. Otherwise, there's literally nothing else in this Y that I can do, right? If I don't have a B, how am I going to proceed to state S? And if I can't get to state S, how am I going to get to state C? So I have to have a B in this loop over here. So I'm going to define this B as the last character of the string, right? So I can still have as many A's or B's or C's as I want, but one of these characters has to pop out and be hard-coded as a B. This is going to allow me now to traverse from state Y into state S. Notice that I'm still going to the left, meaning now I'm going to end up looking at another character from this loop here that gets popped off. Okay. Well, now I see that if I'm in state S, I have three cases. I could read an A, read a C, or read a capital E. All right, so there's two things that I can do here. I can first see, okay, an E is all the way over here. I want to focus on what's here first. I can loop an A and a C onto state S as many times as I want, right? That's what we're doing right over here. So I'm going to pop characters off from this guy and become A or C star. So this A or B or C star, I popped off a B and now I popped off an A or C. I rewrote my answer question, right? So it's as if I originally answered this very vague answer. And then I went over it and I'm like, I could be more specific. I could say A or C star and then a B instead of just saying A or B or C star. So now at some point, right, we're going to end up going backwards over and over and over again. Notice all this stuff is left. We're going to keep going and going and going until we reach the very first character that we ever wrote, which is a capital letter. This is the last question that I have to go over in my test. And I say, oh, the answer needed to be a capital E. What does capital E correspond to? Lowercase b, meaning this first question, I had to answer a B. It can't just be an A, a B, or a C. It has to be specifically a B. So this is going to allow me to rewrite my final regex for except as, I'm just going to write it up here so we have room, B from here, A or C star from over here, and then another lowercase b over here. So now I just write it back from left to right, and this is my final regex. So we've gone from A or B or C, and then A or B or C star as my very vague regex, to now this much more specific regex. So great job, Joe. So we did kind of a lot going on here, right? We went to the right, we went to the left, we rewrote our tape. We're doing kind of a lot of stuff going on here. So when you do these kinds of problems, you want to just try to draw it out, right? If it helps, draw it out as an automaton. That's what I usually advise students to do at first, right? It's as if I go from Q to X, loop on X, then I go backwards into state Y, and I go backwards into state S, right? And I go backwards into state T. So that's kind of what we're kind of looking at over here. And then drawing it out as the tape to ensure that you're going back and forward and rewriting what you already did. Any questions before we go on to reject? Yeah, that's the tricky part. L rejects is where it gets a little bit harder. So I said L rejects is everything that's not L accepts and L diverge. Well, L diverge had nothing. So L rejects is going to be the complement of this guy up here. So if we want to get the complement, right? Once you have a B in the middle, you have a reject. Yeah, so we're going to trace through this and kind of find every place that I can screw up. So my first thing, my first traversal, right? I know that I had A, B, or C, right? We found later on that I had to have a B here. Otherwise, well, I'm not going to have the E and I can never do anything. So I'd have a reject. So the first case that I want to keep in mind, the way I like to do this is break it down into individual cases. The first case that I'm going to do is I'm going to say, what if I don't have a B here? What if my first character is an A or a C? Guaranteed, right? I could have anything I want afterwards. But if I don't have a B here, I'm screwed. That's one case. All right. What about if I had my what if I had my B right at the very beginning? Okay, cool. Went on to X. Okay, I did my A or B or C star. But when I went backwards, I didn't have a B here. We know that if I don't have a B, I get stuck in Y. So then, if I don't have a B at the very end, I have a problem. So even if no matter what's at the very beginning, A or B or C star, if I do not have a B at the end, if the A or C is over here, that's a problem. That's a second case. What about the third case? Well, this case in the middle was saying I had my B here, right? Also, I had my B here, but if I didn't have an A or a C here, okay, well, if I had B's on and on and on, right? Um, what would have happened? Well, the first B would take me to S. But if I don't have an A or a C, right? And let's say that this first character ended up not being a B, right? Um, actually, hold on a second. They have that given. Oh, so actually, this one is kind of a trick. This one doesn't even say write the regex. This is just write 9 distinct strings that belong to L regex. So I could actually stop at this point. I made two cases over here that don't work, right? So I know that if I have an A or a C at the beginning or the end, I don't care what comes after, but I'm screwed at this point. So when you're making strings that work for this, you could keep them as simple as just A, right? A would definitely reject on this, right? Because A comes from this guy up here, right? A and then A or B or C star, right? This is nothing. This is just an A. That's something that would definitely reject. I could have AA, right? Have an A here, have an A here. That rejects. I could create anything from these strings over here, right? This is just saying this or this. In fact, we could even rewrite this. Actually, no, we would have to keep it like that. Yeah, we would keep it like this, right? We would say this or this, right? As a regex, A or B or C, A or B or C star, B. Yeah, that could work too. Um, Joe brought up doing the following. I'll do this in a different color so it's a little easier to see. Um, we could do A, oops, A or B or C, A or B or C star. Guarantee a B in the middle, right? Because the B in the middle would screw things up, right? Because we need A or C in the middle. A or B or C star, and then A or B or C. Yeah, that would work. So these guys are optional, right? Over here and over here, we're guaranteeing that there's a character over here. So at the very minimum, right, if let's say I had B coming from here, a B coming from here, and a B coming from here, right? These two B's are great. They would get us what we need. But the problem is, if I get this B and I go backwards, I can't have a B when I'm going backwards. I need an A or a C star, or that final B to have already been converted to an E. This first B would have been an E. This B would not have been an E. This could not be read by our Turing machine. So this would be a third case to go along with that. So when you're doing reject, I recommend just break it into cases. Do case one, union case two, union case three, and create all the possible ways that you could screw this up. You want to purposely get yourself stuck in whatchamacallit, stuck in like a problem point. Single B also rejects. Yeah, so this is why this question does not ask you to write a regex, because as you can see, it gets really lengthy. The ones that ask you to write a regex on the reject strings usually are much simpler. So bear in mind which ones ask to create a regex and which ones create a just a set of strings. How many questions are on the final? I don't really know the exact number, but it's usually way more than the ones that are given. So if this had like, oh, well, this is the combination of all of them. I would say maybe like 12, 13, maybe even 15 if she wants to give a lot more. But again, you don't need to do everything, right? You aim to get like at least half of them and you should be okay, right? So what I would recommend is kind of go through the exam ones and exam twos, right? And just kind of like try a bunch of them. Like this has 17 questions. That would be like, wait, okay, 16. That's kind of a lot. I don't think an exam would be this long. This would definitely not be it. And especially it would be more like a lot of other stuff too. I would say try to do like one exam from exam one and one exam from exam two and leave it at that. That actually would probably be a lot too, but probably think about like maybe 15 questions max. I wouldn't go more than that. And go all the way from Godels, right? So, um, remember what I had gone over at the beginning. This is kind of like the list of topics, right? All this is from exam one, Godels, regex, context-free grammars, automatons. Exam two is pumping lemma, Turing machines, and the algorithm questions. And then the only new topic that will not be on either is pushdowns. You will need to go through the problem book to find questions on this, or go through my videos. Okay, the last thing I'd like to talk about on this question is the algorithm part. So, where is it? This one. Okay. So over here, right, which language, if any, does the Turing machine M decide? The Turing machine M decides L accepts the language which it accepts because M never diverges. Okay, so decidability, right? This is essentially saying if you have a Turing machine that doesn't uh, diverge, right? Like we know this guy doesn't diverge because it does not have a blank going to the right. Then what language is this aiming to get to the end? Right? We know that the only thing that we can do is L accepts or L rejects from here. That mimics a Turing machine that either halts or diverges, right? It's either or. So that's the decision, right? When we talk about decidability, it's A or B. Do you want vanilla ice cream or do you want chocolate ice cream? Swirl is not an answer in this case. All right. So in this case, right, not decidability, diverging is not even an option here. I either accept or I don't accept, right? To accept or not accept, that is the question. That is literally the question that's here. So this is deciding, do I accept or do I not accept? So that's what we're asking about decidability. If there was a diverging case, if this had blanks going to the right, this state would be my diverging case. This would no longer decide on that matter. It's not either or, right? Now I have three options to choose from. It's not a binary choice. Yeah, decides L rejects as well. So the choice here is L accepts or L rejects. But notice, what is L rejects? L rejects is literally the complement of L accepts. So it says if I'm saying, do I still want ice cream, right? I'm either going for vanilla or chocolate, right? If I don't go for vanilla, I'm guaranteed to go chocolate. If I don't go chocolate, I'm guaranteed to go vanilla. So that's one kind of question that's going on, decidability, right? It's like literally you're choosing between those two things. If it's not this, it's this. Think of a coin flip. If it's not heads, it's obviously going to be tails. I mean, the coin's not going to stand up on like its side or something. Okay. Is L diverge context free? So this is a bit of a tricky question, right? L diverge. Well, we decided that L diverge is just an empty set. It does not exist. So therefore, the empty set, it's regular, right? You could literally write an empty set as lambda. Therefore, if it's, oh, well, it's asking context free. Yeah, this is regular and therefore it is context free, right? We know that all regular expressions are also context free, right? But notice it's not the, actually, I think it would be the other way around. I'm sorry. Um, we know that all context-free, wait, no, it would be the other way around. Sorry. See, it's confusing stuff, all right? All regular expressions can be written as context-free grammars, but not all context-free grammars can be written as regular expressions. This is the key property to keep in mind, right? We know that the empty set, right, it's just the lambda. I can write that as a regular expression, meaning I can also write that as a context-free grammar. If something's regular, it's always going to also be context-free. The key is, if it's context-free, it's not always going to be regular. Now, if this was instead L accepts, this is a regular expression. If it's regular, it's also context-free. This would have also worked for L accepts, right? So pretty much, if they're asking for something being context-free or regular, just remember, can you create a regex out of it? Great, it's also context-free. Think back to your pumping lemma proof, right? That's literally what you're trying to prove there. Then finally, right, we get into the algorithm questions. This is where it gets really confusing, and that's where my guide is going to kind of come in. Explain how to construct an algorithm that solves the following problem. If such an algorithm does not exist, state that it doesn't exist, support your claim, blah, blah, blah. So we're given as input a Turing machine T that decides a language S and a string W. All right, what is decidability? We're deciding, just like with L accepts or L rejects, right? It's always going to be making a choice. So a Turing machine that decides a language S and a string W is W within the complement of S. That's what this is saying. That's what a Turing machine does. You give it a string, it passes the string through the Turing machine, And it says, does the string belong in the accept, reject, diverge case? Right? So when we're deciding something, right, in this case, we're deciding, does W belong in the complement of S? So complement of S is just saying, take the negation of this Turing machine. Literally, take the reject of it. That's the opposite. So if I want to create an algorithm that solves this guy, I'm literally gonna just create a negation of the Turing machine. And that's what this is saying. Again, say it in English. Don't say it in computer science ease, you know? You want to make sure that it's understandable to you. Don't worry about memorizing like everything. Just memorize a template that makes sense to you. So you're literally all this is saying, create the negation of our Turing machine, right? All right. What does that tell us? The Turing machine must halt on W, since T halts on every input as it decides on S. Okay, what does that mean? We know halt, oops. Okay, halting is just equal to not diverging. Sorry, my pen is kind of lagging here. Okay, so this Turing machine does not diverge, meaning that it only halts. Halting is literally L accepts, L rejects. It's doing something. It's ending on some note. It doesn't get stuck on a loop. We know T must halt on W since T halts on every input. That's true, right? This Turing machine is either going to accept or reject. We already proved that. It's going to decide. That's what we're saying here. Because T halts on every input, its complement, the negation, will as well. The best thing to do with these, go through a lot of them. Understand what the pattern is and recognize the pattern. I have a guide over here, right? And this is kind of going to explain it a little bit more. So let's go through this a tiny bit. We're given an input. If the string is an input, if the input is a string or a regular expression, these are called weak inputs. What this means is that we can take them and put them into a deterministic finite automaton. We've done automatons before, right? Whether they're deterministic or non-deterministic has not really been an issue, right? The key here is that if I'm given a string or a regex, I put them into this magical box and I get an output, right? That's what a Turing machine is doing. I'm taking a string or a regex. That is what this Turing machine is doing. If I give them this regex, I accept. If I give them strings, it rejects. If I give them whatever it is, you pass it through. Think of this as a coffee filter. It's going to filter based on whatever I'm given. So we're simulating this through that. Now, this is where it gets different. This is putting a Turing machine in there, not a string or regex. So this is not just filtering, something like that. Turing machines are powerful. They're unpredictable. We need to have an input in the Turing machine. This Turing machine that we had to define our L accepts, L rejects, L diverge. We had to do that. It was not given. So if I have this Turing machine, I didn't decipher it, break it down into these regex. So this is undecidable. Memorize this. That's the first thing to keep in mind. Okay. Second thing, language properties. This is where we get into Rice's theorem, which is very confusing at times, but we'll break it down. All right. Now, if the question is about a property of a set of strings, think of L accepts, L rejects, L diverge, blah, blah, blah. You got to ask yourself this question, is the property non-trivial? This means, is it true for some Turing machines, but not others? right? Trivial, always, 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 always true. Non-trivial, not always true. Think of something. Trivial means, oh, it's something everybody knows. Non-trivial, not everybody knows it. Examples of undecidable properties, right? Is the language regular? Is it empty? Does it contain a string longer than 8? Right? Or some other thing, right? This just cited a specific problem, but if it contains like an infinite string, let's say, right? This cannot be decided upon. And then all you need to say is this answer pattern right here. This algorithm does not exist by Rice's theorem. This is a non-trivial property because blah has it and blah does not. That's it. So they're confusing to read, but if you know how to decipher them, it's a one-sentence answer. So it can be, a little bit of work to decipher it, but if it makes sense to you, recognize what patterns you get, and then hopefully it'll, you can get some points from that. The other property is the membership halting property. This is, does string W belong to the language of Turing machine T? This is going to be a little bit different. If you run this machine, sometimes things loop forever, right? That's your L diverging case. But if this string will actually run correctly, then you know it does halt. But again, sometimes we don't know what this string W is. If we don't know what it is, it may loop forever if there's a diverging case, right? It depends on what is given to us. We need to know, if I put this string into the machine, will it cause it to just constantly loop over and over again? It's as if your computer is just glitching out and it's just going over and over and over again. You have that little loading icon over and over and over again. And all you need to say for this is this algorithm does not exist, which would solve the halting problem, which is undecidable. Right? If we don't know what W is, we cannot decide on it. That's what's going on over here. Okay. Enumeration, right? So, um, sometimes you hear about like recursively enumerable, right? So in a case like this, if you're running the machine, right, and you're able to get that output from it, that target string, then you're good. But if you know that it's not going to print the string, then you know that it's going to not be there. So it's a matter of if the algorithm does exist, but if your string is not going to be in there, right? Okay. So those are the three on that one. And this is kind of just like a little quick table reference to kind of go through that, right? So you're going to see questions with all of these, with all this kind of going on. Have this next to you as you're studying. Go through it, recognize the patterns, right? That's kind of what you're going to be doing in this case. Oh, and then that's just the restart of it. So this is the guide that I have over here, and this is a template for it, right? So again, how to write all of this stuff out, this is how you're going to do it, right? So this is kind of just going through all of these guys over here, right? So if let's say we wanted Rice's theorem, let's say it's asking about a property of set S. Is it regular, empty? Does it have a string length of whatever? Right? This algorithm will not exist because if it existed, it would decide the set of Turing machines whose languages have the following property. You create your characteristic property here, right? And think about it. This property is like the one that we did before, where we said, hey, do I want vanilla? Do I want chocolate? Am I accepting? Am I rejecting? Right? If the algorithm existed, it would decide whether you accept or diverge. Accept or reject. Do you want chocolate ice cream or vanilla ice cream? Right? That's what Rice's theorem is kind of saying. Actually, Rice's theorem, think, do you want brown rice or do you want white rice? We're at Chipotle today, guys. So go into that, and you say that this property is non-trivial. What do we mean by non-trivial? Some know it, some don't. It's true for some Turing machines and false for some other ones, right? So by Rice's theorem, any non-trivial property of a recursively enumerable language is undecidable. Therefore, such an algorithm is impossible, right? Again, you don't have to say it exactly like this, but you have your key points, right? This is your template, just like with pumping llama, but much simpler, right? We're not dealing with like some crazy, really long proof here. So I recommend kind of go through these guys and just kind of recognize the patterns from them, really. That's kind of what it comes down to. So, and again, it might be a lot, it might not be a lot for you. You got to recognize what you're good with, all right? You can skip some topics. You want to aim for getting half the points. So, you could skip a couple topics, but you got to be able to answer at least half the topics very accurately. All right? So just keep practicing, right? If you're better with exam one stuff, focus, focus, focus on these exam one stuffs, right? You want to make sure that you get as many points as possible. Okay. Um, okay, so technically we are out of time, but I will spend a little bit more going over some of the questions that were posted in the chat. So if, Rashawn, if you could send the feedback form if anyone needs to head out early. We just ask if you could fill out the feedback form. That would be nice. But so I could skip those exam two stuff safely. It depends. See, you're gonna end up getting questions like the pumping llama one that we did, where we have to determine if we're doing a language or if we're doing pumping llama. You must, at the very minimum, know when not to use pumping llama and know when to make a language. But keep in mind, if there's like 5 questions on this, right? And let's say there's like 12 questions in total, you still have 7 other questions that you did not answer. So you need to still be able to get some points elsewhere, assuming you get like not perfect scores on all this. I recommend go through exam one, go through exam two, go through pushdown automatons, right? Practice. Take like 6 questions from exam one, 6 questions from exam two, and put a pushdown question in there. That simulates your final exam. And by the way, commonly asked question, you technically do not need to take the final if you are happy with your grade. Use the grade calculator right now. Find what your current grade is. All right. If you got your C or your B and you're happy with your grade, you do not need to take the final. But the final will not hurt you. She essentially drops your lowest grade. So if you don't take the final, that's your lowest grade, that gets dropped. You are an average of your 2 first scores. You got to see what you have and see what you want to do, right? It doesn't hurt to take the final. Chances are the final will be easier than exam two because there's a lot of exam one stuff on there. But there still will be guaranteed pumping llama, Turing machines, algorithms, pushdowns on that thing. So you got to be careful with that. I really don't know the exact number of questions, but I would say maybe 12 to 15. If I had to estimate 12 to 15 questions. So let's say you get 6 from here, and like another one from here or something, give or take. So I can't necessarily, say like, oh, just focus on this because maybe she puts more emphasis on exam one. But what I'm saying is you can afford to not focus on a couple of topics and still get away with it. I'm going to do the questions that you guys post now really quickly. I'm just going to keep the recording going, but I just posted the feedback form in case people had to go since the review session was technically supposed to end at 2. Can you demo the Obrenic calculator for us so people can see how it works? Yes, I can do that for you guys. So I'm gonna put that on. Oh, let me put that on the shared screen that I have here. Okay. So let's say I have, clear this out. Okay. So over here, input your normalized exam scores below. All right. So let's say that I had a 75 on the first, 75 on the second. Boom, you have a B. All right. If let's say I did really bad on this exam, but I did better on this exam, this one gets dropped. This one is good. Sorry, this one is good, and that's my final grade, right? Don't worry about the other attempts. Just you can just do this, right? So pretty much put in whatever your grades are and go from there. So if let's say you got a 40 on this exam, a 40 on that exam, you've established your C, right? Let's say you didn't do too hot. You had a 10 on this one. Let's say you had a 20 on this one, but you locked in and you got a 40 on that one. Okay, maybe not that, but okay, let's say 20, 20, and a 40. Okay, because this exam 3 is a little bit more points. So I think I'd have to go a little higher on that. Let's say I had a 50 on that. Okay, there you go. So the 20 and the 50 average out to be your 40. So play around with it, right? See how your exams are and see what you need to get on your final grade, right? If I recall correctly on mine, I think I had like I think I got like a 70 something, maybe like a 75 on this one. I think I had like a 60 on this one. Or actually it was higher because I had a solid B plus, I think. But on exam 3 I locked in and I think I got like a yeah, I think I got like a 90 or something because that got me into the A range. So again, exam 2 is probably the harder one. You know, you have like a lot of stuff kind of going on there and everything with pumping lemma and Turing machines. So like even if you didn't do hot on this, you know, you take your two highest scores. So if that's exam 1 and exam 3, then you can do very well for yourself. And there are people who like literally take one exam and are able to pass. Like if I have like a, it's like the lowest I could get on this and still pass. Like a 70 on this one exam, probably. Actually, maybe even a 65. 60? Okay, yeah, you could literally get a 55 on exam 3, not take any of your other exams, and still pass with a C. Obrenic's class is very passable. It's not easy, but it's very, very passable. You can slack off on all the other exams and still take one and literally get your passing score from that, right? So this 55 literally means I got like a little bit more than half the questions completely right. So again, focus on getting at least about half the questions. If you're good with that, play around with your score. See what you need to get the grade that you want. And if you're happy with your grade after the two exams, whatever this grade is, and after these two, you can walk out with that. All right? If you got your B after getting a 70, 75 on these two, and you got your B and you're happy with that, take it. Relax. Don't worry. You've passed. You've done whatever you needed to do. But if you want, take the final. You can only get higher. I took it, got me in the A range, so I was happy. Not that a B wasn't good, but you know, if you can have the chance to get a higher score, take it. Questions about that before we spend the last couple of times to go over some more questions that people had? Yeah, don't say you're gonna bomb the class, all right? It's very passable. I mean, you see. it's hard questions, but if you know where to get the points, you're gonna be all right. So let's spend a little time going over some of the questions that people asked for, and then we'll wrap up for today. So I'm hoping to maybe be done by like 2:30, quarter two. But if you have to go, just fill out the not attendance, well, if you didn't fill out the attendance form, please fill out the attendance. If you have feedback, please fill out the feedback form. Alrighty. So we got some regex going on here. We got some more regex, and we got some godels. All right, I'll do one of the regex ones. Let's do this one over here. You could see this question, right? All right. So we'll do that. There's a Gödel number question as well. I could try to do that really quick. Grammar. And that's another regex. Okay, actually that's the same one. All right, so I have this one-page regex. There's a Gödel question, and then there's a grammar question, and then we'll finish off from there. All right. So we're going to start off with these. These are the one-page easier regex questions. I'm not saying everything's easy here, but it's easier to get some points, right? This is a solid 12 points. So 1, 2, 3, 4, 5, right? Even if you only do like a couple of them, you can easily get some good points out of this. So we have the set of exactly those strings over sigma that contain at least one of the substrings BBC, GAA, but the letter G occurs exactly once in the string. I was stuck at the other regex problems part A screenshot. You want me to do the other one? I'll do the other one. This one over here, right? Yeah? Okay, got it. We'll do this. Just out of the essence of time. Okay. So over here, exactly those strings that begin with A or B end with either C or G, but always contain at least one G. All right, so the first step with these is, okay, I will do both then. All right, we could do it. So first, we want to start with what is absolutely necessary. All right, I know I need an A or a B at the beginning, something, 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 and a C or G at the very end. Okay. Now, here's the problem though. Contains at least one G. Okay. So this is telling me that if I have the G at the very end over here, right? Then at that point, technically, I don't need to include a G somewhere guaranteed here in the middle, right? So if this I select a G for, this middle part does not need a G. I could just use A or B or C or G, right? But if I don't include the G here, if I choose the C instead, then I have to guarantee a G is somewhere in my string. And that's going to leave me with A or B. Anything I want here, I'm just going to use sigma just to save some space. Anything I want here, and then finishing off with C. So the way that this answer ends up looking is we break it into two cases. One of them, I choose C. One of them, I choose G at the end. Both of them have A or B at the very beginning. The problem here, though, is if I just said C or G at the end here, and if I said A or B or C or G star here, if I left it like this, what if I don't choose G? And what if I don't choose G? That does not guarantee that there's a G in that position. So I have to go into both cases. I have to consider the case if I do choose the G, then A or B or C or G star can just go here without any problems, right? So if I choose the G, if I don't choose the G, does not matter. But if I did not choose the G in this position, if I chose a C in this position, if I did not choose the G here or here, I have to guarantee that the G appears somewhere around here. So we break this into the two conditions here. Does that make sense? We want to kind of see what is absolutely necessary and work around the string. It helps to break things down into multiple cases separated by a union. Yeah. So I know I have to begin with A or B and I have to end with a C or G. Okay? That makes sense. But I have to guarantee to have at least one G. The problem is if I have C or G at the end, that's saying C or G. It's not guaranteeing that there's a G at the very end. So I have to take into account if I have a G at the very end, right? That's this second case. Then I don't have to guarantee a G somewhere in the string. If I chose the first case, which is a C at the end, then I do have to guarantee a G. And all this is just saying is a guaranteed G, anything I want before, anything I want after that G. Because A or B or C or G has a star, so it's not guaranteed that I have a G. So we break that down into two. If the end was not either C or G, if it was only G, then I would not have to have worried about breaking it down into two conditions. Then I could have pretty much just had up here and called it a day. So that was a bit of a trickier one. Yeah, these are tricky. And you got to consider edge cases a lot. It's a lot of ones here that are going to have edge cases. So let's see if one of the other ones has one of those kind of edge cases to think about. Honestly, the more you do of these, the better that you're going to get at recognizing these tricks. You know, okay, if you don't get the first part, but you get the others, you're still going to get points, right? All right, maybe you get 9 points instead of 12 points. That's still a lot of points. Focus on what you know you can do. Oh, part A is kind of tricky. Let me do part B. Let me do part C. Let me do part D. Even if you only get 3 points out of one of them, right? She gives multiple of these. That way you're able to pick and choose what you want to do. So part B, exactly the strings whose total numbers of B's and G's, right? So this is just saying the number of B's plus the number of G's is not greater than 2. So this is one of those other cases that I got to think about. So the number of B's and G's, okay, I could have 0, I could have 1, I could have 2. It can't be greater. So I could literally rewrite this as a couple of different things. I'm going to do it the brute force way that might be a little more obvious, and then I'm going to do it the way that she did it. I could just have 0 B's and G's. That's just A or C star, right? Just non B's and G's. That's my 0 case. Union that with my 1 case. My 1 case is exactly 1 B or G surrounded by non-B's or G's. My pen is really lagging here. Sorry about that. So this should be A or C star, right? And then A or C star. Okay, my pen is seriously lagging. There we go. So I'm surrounding a single B or G with A's and C's. Lastly is 2, right? So I union each of these cases. This one is 2 B's or G's, right? And in between are going to be my A's and my C's, right? Okay, it's seriously lagging here, but these are my A's and my C's in between. Okay. So I can union these three cases. Or I could simplify it a little bit and do it similar to how she did it, right? And what she did here was she said B or G or a lambda, B or G or lambda. So this is saying choose a B, choose a G, choose a lambda. So I could end up having a lambda here and a lambda here. Boom, I get my zero case. I could choose a B here and a lambda here. I get my one case. I could choose a B here and a B here. I get my two case. So writing it out as a character or a lambda allows me to say choose it or don't choose it. And I can write it out a little bit smaller than if I wrote out all three of these cases unioned. But this is totally right. Make sense? So part C now, the set of exactly those strings over sigma whose length is no less than 2, where the first leftmost symbol is different from A, the second symbol is different from B, and the last symbol is different from G. Okay, a lot of stuff going on here, right? So let's lock in what we need. The first symbol is not an A. So I'm going to have B or C or G right there. The second symbol is not a B. I have A or C or G. Now, the last symbol is different from a G. Okay, so I'm going to have anything I want in between, and then just not of a G. But now I got to think about, well, what if I have a small string? What if I have a string that is no less than 2? What if it's actually equal to 2? So what if I have the first symbol is different from an A, and the second symbol and the last symbol are just the same? What if I have a string that looks like B, B? That works, right? So I could do something kind of, oh, sorry, the second symbol is different from a B, so this second symbol can't work. I'd have to do something like BC. So this is telling me that instead of having a string guaranteed length of 3, what if I just have one that's a string length of 2? I have a non-A here, and then my second symbol is also my last symbol. So it's not a B and not a G. Therefore, it's A or C. So this is one of those edge cases that you got to keep in mind. So this could have also been worded. What if it was whose length is no less than 1, right? Well, what if I have a string that's going to be 1 in this case instead? Well, the first symbol, oh, well, the second symbol has to exist. But let's say the first symbol and the last symbol, if the first symbol is A and the last is different from A and the last is different from G, then I could have a string that has B or C. That could work. So keeping in mind these edge cases is going to be a major thing on the exam with these regex. Okay, divisibility. This is the part D. The total numbers of A's and C's is not divisible by 3. All right, so not divisible by 3, meaning it could be divisible by 0, it could be divisible by 1, or it could be divisible by 2. Actually, would be 1 or 2, right? So I can't have it divisible by 3. So the total numbers of A's or C's, right? I'm going to have either 1 or I'm going to have 2. And that's kind of what we're going to be having over here, right? I could either choose to have divisible by, this is going to be our loop over here. I could choose to either have, actually 0, to be honest, 0, 1, or 2 A's and C's. So this part, B or G, is going to be the 0 case. Then I'm going to have the part with 1, right? So over here, or actually, I'm sorry, I'm looking at the wrong thing over here. Let me restart from the beginning. Okay. So if we want things to be not divisible by 3, right? I want to always make sure, yes, it's still recording, don't worry. I want to make sure that I either have 0, 1, or 2. Okay, so if I have a number that is not divisible by 3, right? I want it to be divisible by 0, 1, or 2. I could first take into account this part over here. This is going to show my 0, my 1, or my 2, right? Actually, it would just be my 1, sorry. My 1 or my 2. Sorry, because 0 would end up just being divisible by 3 because 3 divided by 0 is 0. So what I have here is my 1 mandatory A or C right here. My second one looks like this, right? This is the same case that we did earlier here. I could choose an A and then I could choose a lambda. That's my case 1. I could choose an A and then I could choose a C. That's my case 2. Each of these is being surrounded by a B or G star. So this has 1 or 2. Now, if I want to keep this relationship, I can add 3 to it repeatedly. If I have 1 plus 3, this is going to give me 4, right? Still keeping the relationship. If I have 2 plus 3, that's going to be 5. It's going to keep the relationship. So if I constantly add 3, then I'm good. And that's exactly what I'm doing over here. I'm adding 1, 2, and 3, and I'm just separating it with B's and G's stars, right? So this is going to end up having a 3n plus 1 or 3n plus 2 relationship. So that's our key here. And this is a very common question she might ask. If she asks for something even versus odd, right? Even is always going to be 2n. Odd is 2n plus 1. Because think about it. Any even number is just, any odd number is just an even number added with 1. Same thing happening here. 3n plus 1. Divisible by 3, we make it no longer divisible by 3. Divisible by 3, no longer divisible by 3. Okay. So then finally part E, the set of exactly those strings that contain at least one substring length equal to 2, such that the 2 letters in the substring are different from one another, but neither is B. Okay, this one you gotta kind of brute force. You're gonna write out every possible substring where the letters are different, but neither is B. So AC, AG, CA, CG, GA, GC. Surround it with anything you want at the beginning or the end, right? So you're guaranteed to at least have that guaranteed substring and just surround it with whatever else you want. We don't care about anything else. We just care about this mandatory part. So the trick with these regex questions, find the mandatory part, find your base cases and your edge cases, and then add in anything else that you might need. Okay, so that is the one regex question. I'm going to rush through this one a little bit quicker, just in the essence of time. The set of exactly those strings over sigma that contain at least one of the substrings BBC, GAA, but the letter G occurs exactly once in the string. Okay, so again, different cases. If I choose this substring, then I must guarantee G occurs somewhere else. If I choose the second substring, I do not need to ensure that G occurs because the G is already in there. So let's go through the first one. I choose the first, BBC. I surround it with any non-Gs that I want. So again, G only occurs once. I have a mandatory G. I have anything else I want. But think about it. The order could be reversed. What if I have the G on this side instead? That's my second case. I put the G on the left and the BBC on the right. Then, if I didn't choose the BBC and I chose GAA, well, this one's even simpler. I choose GAA in the middle and I surround it with anything else I want. That's the first part. Part B, the set of exactly those strings over sigma where the total number of occurrences of letters that are different from G is greater than 2. So different than G is greater than 2, meaning we have to guarantee at least 2 greater than 2 non-Gs. So non-Gs are just going to be A or B or C. So I'm going to guarantee A or B or C, A or B or C, A or B or C, right? So we guarantee that this happens, and then I could have anything I want afterward, right? Technically, I could have replaced these G stars with this as well, A or B or C or G star. That's totally fine as well. There's nothing saying that G's have to be in this place. So in this case, remember, have your mandatory ones, non-Gs, and then surround it with anything else. Okay, part C. Exactly those strings whose length is no less than 3, where the first leftmost symbol is equal to the last rightmost symbol, but different from at least one other symbol in the string. Okay, write down what we need. The leftmost is equal to the last rightmost. So I could have A something A. I could have B something B, C something C, G something G. Okay, different from at least one other symbol in the string. Now we must guarantee that if I start with an A, I have a non-A somewhere in the string. So that's what we're doing here. We have A, non-A, finish with an A. B, non-B, finish with a B. C, non-C, finish with a C. G, non-G, finish with a G. And just like before, we fill up the middle parts with anything we want. We really don't care about that. So we start with what we need and we add in what else we can put in there. Okay, the set of exactly those strings over sigma where the number of B's is even. What is the formula for even? 2n. Therefore, I'm going to end up having B and B in a loop, right? So that's what I'm having in this part here. BB in a loop, right? And honestly, I don't even know why she wrote it like this. I would literally just write it as B, A, or C, or G star. Okay, why is this pen not working still? Okay, B, A, or C, or G, B star, right? Oh, and then to be honest, right? Well, if B's are even, technically 0 B's is also even as well. So I need to also have a case in which I just have no B's. And that's just A or C or G. So I could write the second half of this as A or C or G star. And the way that she has it is she just puts both of these into a star. So instead of having a star here and a star here, it's just in one regex. That's kind of fine too. Both of these are completely valid. Okay, and finally the last one substring of at least length equal to 3, such as all letters in the substring are different from each other and occur in the alphabetical order in the substring. Okay, so think about the ways that we can word this, right? I could have substring A, B, C. It's length of 3, they're all different, and it's in alphabetical order. A, B, G, also 3, alphabetical order. A, C, G, B, C, G, all those work, right? I can't have something like CGB because they're all out of order. I can't have something like BBBBB because there's 4 B's in that case, right? Again, we ensure that these 4 are set and then surround it with anything else that we want. What we need, and then put anything else around it. That is the end of the regex part. Yeah, just write it in the way that makes sense to you. If you want to brute force it, do it brute force, as long as it's correct. So honestly, like, stick to whatever makes it easier for you. All right, this Gödel question is very, very similar to the previous one. And I'm not going to go through the whole thing, but I'm going to explain why this is the case that it does not exist. Gödel number is divisible by 54 and 55, but not by 42. So same thing as we did at the very beginning. We're going to take the prime factorization of 54 and 55 and 42. Okay, we know that the prime factorization of 55 is 5 times 11. We know that the prime factorization of 42 is 2 times 3 times 7. But this is the problem. If I need 5 and 11 and I don't want 2, 3, and 7, I need 2, 3, and 7 in order to get up to 11, right? So I can't write a prime factorization for 55 without writing 42 in there. We don't even need to worry about 54 at this point. Having 55 divisible but not by 42, that's our problem point. Because we can't skip primes. I need 2, 3, 5, 7, 11. 2, 3, 7 is in that prime factorization if I'm trying to do it in Gödel numbers. Okay. Any other questions before we wrap up? I think I'm gonna call it here. All right, so listen, just kind of keep practicing with these. There's one more screenshot. Uh, oh, this one over here. Okay. I'm gonna skip the grammar part of this. I'm assuming this is the part that's definitely more confusing in this case. So I'm gonna focus on this part, right? Because I think at this point the grammar shouldn't be too bad for it, but combining it into this craziness is probably gonna be the part that people are gonna be questioning about. So we know we have language one, language two, right? Oh, the problem wording. Oh, oh, okay. Okay, let's just start from the beginning then. Okay. So if we have one of these that's kind of crazy looking like this, we're going to underline what's kind of going on here. Let's focus on L1 to start. So the length is equal to 4n plus 1. Okay. The symbol in the middle of the string is different from is different from C and different from G. Furthermore, there are no A's before the symbol in the middle. Okay. So if I'm going to draw this out, 4n plus 1, I'm going to have one symbol in the middle, and I'm going to have four symbols surrounding it. 1, 2, 1, 2. Because this has to be in the middle. So I'm going to have 2 on this side, 2 on this side. The symbol in the middle of the string is different from C and different from G. So that means that this can only be an A or a B. There are no A's before the symbol in the middle. So that means these two symbols can either be B, C, G, B, C, G. These guys, though, can be anything in our sigma. So that's how we're going to interpret that. Now we can actually create the grammar out of this, right? So what I'm going to do is we know that the middle symbol is going to be an A or a B. So I'm going to create a function to define the left side, which are going to be B, C's, and G's. And I'm going to create a function on the right side to just show any letter because there's no restrictions. So that's going to be A, which is going to stand for a B, a C, or a G. So any non-A's. We're going to recurse on our S, and then we're going to call ZZ, which is anything we want because there's no restrictions on the right side. So as this goes, it's going to telescope outwards. So if I telescope this once, right, I have A, S, ZZ. I telescope it again, I'm going to get another AA on the left and another ZZ on the right, right? And I'm going to constantly go outwards and outwards. That's why we call it telescoping. At the very end, once I'm done, my end cases are going to be just A or B because it tells me that the middle symbol has to be different from C and G, meaning the middle symbol is going to be A or B. So that's what this grammar over here is going to be. Does that make sense? So kind of breaking it down case by case, drawing out what it looks like helps a lot. And I know from here, I can make this into a function and this into a function. And that's how we define these two guys. Now, on the other hand, L2 be exactly those strings over sigma where every occurrence of C is followed immediately to the right of it by a substring of length equal to 3, such that none of these three symbols is C. Okay, so this is telling me anytime that I have a C variable, I must have a substring here. Okay, so this substring needs to be its own function for sure. So if I have a C, I must follow it by, let's call this function A. This function A is going to be length equal to 3. None of the three symbols is C. So I could just have a non-C here, here, and here. I'm going to define the non-C as function B. So function B now is going to just be A or B or G. So anytime that I have a B, B, B in this substring, this is telling me that anytime that I have a C, I call function A, which is just going to be 3 B's. And each B is just going to be a non-C. So that's how we're going to define this grammar over here. Now, otherwise, I'm free to pretty much put anything else that I want, right? So from here, I could just rewrite that as A, B, G, but then I must have a C with my function. So she did not make the three B's into their own function like how I did with A, but you can do this too, right? This is just saying B, B, B. B is just a non-C. So I'm constantly recursing over myself, right? And I'm saying every time that I call this, either have an A, a B, a G, but if I end up with a C, I need three B's after it. Three B's being the function giving me no C's. Okay, does that make sense before we go on to the next part? Did we go over anything similar to this with the Z in the middle? Yeah, I think we did earlier on. So if there's ever something in the middle, right, you kind of want to recurse outwards. That's kind of similar to what we did up here. An A and a B had to be in the middle. So that's what this S is saying. I'm recursing outwards and outwards, and once I finish, I have an A or a B in the middle. So in that case, the question was saying a Z. You could put anything you want in between. But this is just saying my base case is going to end up being in the middle here, and it's going to be an A or a B. Okay. So let's go on to the last part of this. So when we have something that looks like this, where we're combining different parts of our languages, right? All we're doing is taking these pieces that we defined, the actual languages, and defining them into this over here. So L1 star is saying, take my L1, which is this guy here, this S, and I'm just going to call that recursively. So instead of calling this S, right, let's just say I call this L1, right? So L1 is going to be the variable that defines my string 1. What I'm going to say is I'm just going to call that recursively. I'm going to say L1, L1, or lambda, right? That's exactly what we have over here. It doesn't look like it, but Q is being defined as our L1. We're setting some variable equal to it, right? And same thing for L2. I can create another variable for L2 right here. Let's say R is what they did. Lambda RR, right? So I'm choosing between L1 star, Q, L2 star, star or the concatenation between both of these guys star. So now instead of having L1, L1 lambda, I'm going to have L1, L2 lambda, right? Oh, sorry, L1, L2 are concatenated, right? So these two concatenated, and I'm able to loop on this, right? Because I got my lambda going on here. So that's kind of what we're dealing with these guys, right? Instead of just taking a function, though, we're defining the entire language as its own function. So we're going outside one extra layer, and we're defining each of these guys, each of the languages, as their own function. And then otherwise, all this is just the same, right? This we're just taking from here. We might just have to change the name of some of the functions, right? Because, if you have an A defined in L1 and an L2, then you just got to change it. But otherwise, besides the name, everything else is exactly the same, right? We break it down. That's like our L1, and that's our L2. Will this type of question appear on the final exam? Maybe. You could expect any of the context-free grammars, any of the regular expressions, any of the thing. So just kind of, do as many as you can. Go through as many as you can, and you'll find that you get better as you improve. So we kind of went over a lot over here. But so I'm gonna end it at this point. Um, but yeah, if you guys have other questions, feel free to ask in the chat and keep practicing, keep going over the stuff, and best of luck. Yeah, of course. Hope this was able to help, and yeah. Make sure if you haven't filled out the feedback form, please fill it out before you leave. And I hope you guys have a nice day. Oops, I just sent that as a direct message. Yeah, so let me end the recording here.